Day 15 of 60. Today we are covering load balancing algorithms. Not the textbook definitions, but which algorithm you actually pick for which production workload and why. Load balancing is one of those areas where the wrong choice stays invisible until traffic spikes and your pager goes off at 3 a.m. Let us start with round robin. It is the default in Nginx, HA proxy, and pretty much every load balancer. Requests go to backends in sequence. Server 1, Server 2, Server 3, back to Server 1. Zero state tracking, zero overhead, perfectly predictable. When your fleet is homogeneous and request durations are roughly uniform, round robin is the correct choice. Weighted round robin extends this for mixed hardware. If Server A has 4 CPU cores and Server B has 8 cores, you assign weight 3 to A and weight 5 to B. In Nginx, this is just the weight parameter on each server directive. The proxy_next_upstream directive is critical here. Without it, if a backend fails, the client gets an error. With it, Nginx automatically retries the next server in the rotation. Least connections. This is where round robin breaks down. Picture an API serving both quick config lookups that finish in 5 milliseconds and complex report generation taking 30 seconds. Round robin treats these equally. One server gets stacked with long-running reports while others sit idle. Least connections routes each new request to the backend with the fewest active connections. In HA proxy, you set balance least con. Pair this with health checks. The fall parameter sets how many consecutive failures mark a server as down. Rise sets how many successes bring it back. I typically use fall 3 rise 2. This prevents flapping during transient network errors. The inter parameter controls how often health checks run. 5 seconds is a reasonable default for most services. IP hash and sticky sessions. Some applications store session state in server memory. Shopping carts, WebSocket connections, partial file uploads. IP hash routes all requests from the same client IP to the same backend. In Nginx you just add IP_hash to the upstream block. Here is the trade-off. Sticky sessions create uneven load distribution. Corporate NATs funnel thousands of users through one IP, so one backend gets hammered while others are underutilized. They also complicate deployments. Draining a sticky server means waiting for all sessions to expire or actively migrating them. The production answer, almost always, is to externalize session state to Redis or Memcached and use a stateless balancing algorithm. If you absolutely must use sticky sessions, set reasonable TTLs and monitor the load distribution across backends. Consistent hashing. This is essential for caching layers. With standard hash-based routing, you compute hash of the key mod n where n is the server count. Add one server and n changes, which remaps almost every key to a different server. For a Varnish or Redis cluster, that means a sudden storm of cache misses. Consistent hashing arranges servers on a virtual ring. Each server owns a range of hash values. Adding a server only remaps keys in its immediate neighborhood. In Nginx, you add the consistent keyword after hash and the request URI variable. That single keyword switches from standard modular hashing to Ketama-style consistent hashing. Without it, every topology change scrambles your cache hit rates. Power of two choices. This algorithm is underrated in practice. Pick two servers at random, check their current load, route to whichever has less. Research by Michael Mitzenmacher proved this gives exponentially better maximum load bounds compared to pure random selection. The key insight is why this beats global least connections at scale. When you have multiple load balancer instances, each one tracking connections independently, they can all simultaneously decide the same server is the lightest and create a thundering herd. Power of two choices uses local randomness to break this correlation. In HA proxy you configure this as balance random with the parameter 2 in parentheses. It is particularly effective for large distributed fleets with multiple balancer instances. L4 versus L7 and connection draining. L4 balancing works at the TCP layer. It forwards packets without reading their contents. Fast, simple, works with any protocol. L7 balancing reads HTTP headers, URLs, cookies. You need L7 for path-based routing, header-based canary deployments, and TLS termination at the balancer. Connection draining is what keeps deployments from dropping requests. When you remove a server, stop sending new connections but let existing ones finish. HAProxy's slow start parameter ramps traffic to a freshly healthy server over a configurable window, say 30 seconds, instead of hitting it at full weight immediately. Cold JVM heaps, empty connection pools, and unprimed caches all benefit. Combine draining and slow start for zero downtime deployments. Quick selection guide. Homogeneous fleet with uniform requests, round robin. Mixed hardware, weighted round robin. Variable request durations, least connections. Caching layers, consistent hashing. Large distributed fleets with multiple balancers, power of two choices. Sticky session requirements, IP hash, but make a plan to migrate to stateless. And health checks are non-negotiable regardless of algorithm. A load balancer routing traffic to dead backends defeats the entire purpose. That is day 15. Tomorrow we cover auto-scaling strategies and how load balancer configuration adapts when backend pools change dynamically.